When we say the universe might already be dead, we confront a concept that defies intuitive understanding. Death typically implies cessation, a living organism stops functioning, consciousness ends, processes halt. But the universe is not a biological entity with clear boundaries between life and death. Instead, being dead for the universe could mean several things. It might mean that the fundamental processes driving cosmic evolution have already completed their most important work. It could mean that peak complexity has passed, and entropy now dominates irreversibly. It might mean that what we perceive as dynamic change is merely the slow unwinding of processes that effectively concluded long ago. Or it could mean something even stranger, that time itself is an illusion and the universe exists in a static state we mistakenly perceive as evolving. The concept of a dead universe challenges our temporal perspective. We experience time flowing from past to future with clear directionality. We observe stars shining, galaxies moving, and processes occurring that suggest ongoing activity and life. But this perception operates on human timescales, decades, centuries, millennia at most. Cosmic timescales span billions of years. On such scales, what appears dynamic might actually be static. A star that will shine for 10 trillion years seems eternal from a human perspective, but on cosmic timescales, it represents a brief flicker. If the universe's total lifespan spans 10 to the 100th years or more, then the current epoch, 13.8 billion years after the Big Bang, might be cosmically equivalent to the first microseconds after conception for a human life. Or conversely, it might already be the final moments. One interpretation suggests the universe is dead in the sense that its fate is already determined. General relativity and thermodynamics together imply that given initial conditions and physical laws, the universe's entire history from Big Bang to heat death unfolds deterministically or probabilistically according to fixed rules. In this view, the universe resembles a movie that has already been filmed. We experience it frame by frame, but the entire sequence exists timelessly. The ending has already been written, even if we have not yet experienced it. From this perspective, the universe is dead because it lacks genuine spontaneity or freedom. Everything that will happen is already encoded in present conditions and laws. The future is as fixed and inevitable as the past. Another interpretation focuses on energy availability. A living universe is one where free energy available to perform work remains abundant. Dead universe is one where free energy has been exhausted or dispersed so thoroughly that no interesting processes can occur. Thermodynamically, this corresponds to maximum entropy equilibrium, where all energy exists at uniform temperature with no gradients to drive change. We are obviously not at maximum entropy now. Stars shine, life exists, structures persist. But the second law of thermodynamics guarantees entropy increases irreversibly. Every process that occurs, every star that burns, every thought that forms, every particle that moves, increases total entropy. The universe marches inexorably toward entropic death. If this march cannot be reversed or halted, then in a meaningful sense the universe is already dying, and its death is merely a matter of time. A more radical interpretation questions the nature of time itself. Physics presents multiple views of time's reality. The block universe interpretation of relativity suggests all moments in time exist simultaneously in a four-dimensional space-time block. Past, present, and future are all equally real. Our perception of flowing time is an illusion created by consciousness moving through the block. In this view, the universe does not evolve or change. It simply exists as a complete four-dimensional structure. Birth and death, beginning and ending, are just different regions of the block. The universe is neither alive nor dead, in a temporal sense because it does not exist in time. Time exists within it as one of its dimensions. From this perspective, asking if the universe is already dead is like asking if a mountain is already climbed. The mountain exists with all its heights simultaneously. Whether you perceive it as climbed depends on where you are on the slope. Quantum mechanics introduces additional strangeness. Some interpretations suggest reality is fundamentally probabilistic until observed. The universe might exist in quantum superposition of multiple states simultaneously alive and dead, beginning and ending until conscious observation collapses wave functions into definite states. Before observation, the universe has no definite properties. After observation, it retroactively acquires a definite history consistent with our observations. This raises the unsettling possibility that the universe's state, including whether it is alive or dead, depends on observation. Without observers, the universe might not have determinate existence at all. As observers dwindle in the far future, perhaps the universe fades from definite existence back into quantum uncertainty, dying not through physical processes, but through lack of observation to sustain determinate reality. The question of whether the universe is already dead ultimately depends on definitions. If dead means lacking change, the universe is clearly not dead. Stars evolve, galaxies collide, structures form and dissolve. If dead means fate already determined, then yes, physical laws imply determinism or probabilistic determinism that fixes outcomes. If dead means maximum entropy equilibrium, then no, we are far from that state. If dead means existing timelessly rather than evolving, this depends on interpretation of time's nature. Physics permits both views. What makes the question interesting is not finding a definitive answer, but exploring what different answers reveal about time, consciousness, entropy, determinism, and existence itself. The universe might be dead in some senses and alive in others, or the distinction might be meaningless when applied to the totality of existence rather than entities within existence. The illusion of the present moment. The present moment feels immediate and real. We experience now as a singular instant separating past from future. But physics reveals no such instant exists objectively. Relativity demonstrates that simultaneity is relative. Events that appear simultaneous in one reference frame occur at different times in another frame, moving relative to the first. There is no universal now spanning the cosmos. The present moment is a subjective construction of consciousness, not an objective feature of reality. What we call now is a perceptual artifact created by our brains, assembling sensory data, memories, and predictions into coherent experience. The cosmic present does not exist, only our local, limited, relative present that extends perhaps a few hundred milliseconds around our immediate sensory experience. Light speed imposes fundamental limits on the present. Light from the sun takes 8 minutes and 20 seconds to reach Earth. When we see the sun, we observe it as it was 8 minutes ago. If the sun exploded this instant, we would not know for 8 minutes because information cannot travel faster than light. In a meaningful sense, the sun, as it exists right now, is not part of our present. It lies in our future, beyond our light cone, causally disconnected from this moment. Similarly, we exist in the sun's future. The sun as it exists now cannot see Earth. Earth now lies in the sun's future light cone, observable only after 8 minutes elapse. Our presents do not overlap except in the past. This temporal disconnect becomes dramatic at cosmic scales. The Andromeda galaxy lies 2.5 million light-years away. When we observe Andromeda, we see it as it existed 2.5 million years ago, before modern humans evolved on Earth. Andromeda, as it exists now, is completely unknown to us. It might have been destroyed by a gamma-ray burst, merged with another galaxy, or developed advanced civilizations. These events lie in our future light cone. We will learn about them only when photons carrying that information arrive in 2.5 million years. Conversely, from Andromeda's perspective, if observers exist there, they see Earth as it was 2.5 million years ago in the Pliocene epoch. They cannot know about modern humanity, cities, or technology. Our present moment is Andromeda's distant future. The observable universe extends to approximately 46.5 billion light-years. Light from the most distant galaxies has been traveling for over 13 billion years since the universe was young. We see these galaxies as they existed shortly after formation, small, irregular, actively forming stars. But those galaxies, in their current state, exist far beyond our present. They have evolved for 13 billion years since emitting the light we now receive. They might be large ellipticals, might have merged with others, might no longer exist. Their present is our far future. We observe only their ancient past. The entire observable universe as we see it is a historical record, not a present snapshot. Every photon carrying information about distant regions left its source in the past. The farther we look, the deeper into history we peer. This means the universe we observe is already dead in the sense that it no longer exists in the form we see. The cosmic panorama we observe through telescopes is a patchwork of different eras: the Sun, as it was 8 minutes ago, nearby stars from years to decades ago, distant galaxies from millions to billions of years ago, the cosmic microwave background from 13.8 billion years ago. None of these objects exist in the states we observe. We live in a universe of ghosts, images of things that were but are no longer. The present cosmos as it actually exists this instant is completely hidden from us by light speed limits. We can never observe it. By the time light from distant regions reaches us, those regions have evolved into new states we cannot yet see. Consciousness compounds the illusion. Neuroscience shows that conscious awareness lags behind events by approximately 80 to 500 milliseconds. When you catch a ball, your brain predicts where it will be and moves your hand accordingly before you consciously experience the decision. What you perceive as the present moment is actually a reconstruction of the recent past, assembled and edited by neural processes to create a coherent experience. Your present is your brain's best guess about what just happened, smoothed and integrated to feel instantaneous. Even within your body, the present is an illusion created by information processing delays. If there is no objective present moment, and what we experience as now is merely assembled past data, then in what sense does the universe exist in the present? It does not. The universe exists as a four-dimensional structure in space-time, with all moments equally real, but inaccessible from other moments. We are embedded in this structure, moving along our world lines through time at 1 second per second, assembling experiences from past light cones and calling the result the present. But this present is a fiction. The cosmos has no now. It has only the eternal four-dimensional structure containing all events past, present, and future from any local perspective in timeless coexistence. The universe we observe is always already dead because it is always already past. We live in memories, experiencing a universe that has moved on beyond our perception, light from dead stars, ancient photons. Most stars we see in the night sky no longer exist in the form we observe. Some have evolved, some have died, some have been destroyed. Light travels at finite speed, creating an inevitable delay between emission and observation. For nearby stars like Sirius, located 8.6 light-years away, this delay is modest. The Sirius we see is how it appeared 8.6 years ago. Given stellar lifetimes of millions to billions of years, this delay is negligible. Sirius in its current state, differs imperceptibly from how we observe it. But for more distant stars, the temporal gap widens dramatically. Betelgeuse, the red supergiant marking Orion's shoulder, lies approximately 550 light-years away. When we observe Betelgeuse, we see light emitted in the 1470s while Earth was in the Renaissance. Betelgeuse currently might have already exploded as a supernova, an event we would not observe until the 2,570 seconds. The temporal disconnect becomes extreme for objects in distant galaxies. Supernova SN 1987A, discovered on the 23rd of February 1987, occurred in the Large Magellanic Cloud, approximately 168,000 light-years away. The explosion we observed in 1987 actually occurred 168,000 years earlier, roughly when modern humans first emerged from Africa. The star that exploded has been dead for over 150,000 years by the time light reached Earth. We watched ancient light from an event that finished millennia before human civilization began. Every photon we detected was a messenger from deep prehistory, carrying information about a star that no longer exists. The supernova remnant continues, evolving shockwaves expanding, neutron star forming, elements dispersing, but we will not observe these developments for thousands of years more. The farthest observable galaxies lie approximately 13.4 billion light-years away, seen as they existed merely 400 million years after the Big Bang. The light we receive from galaxy GNZ11, one of the most distant known, left its source when the universe was only 3% of its current age. These early galaxies appeared small, irregular, filled with intensely hot young stars, but that was 13.4 billion years ago. GNZ11, in its current state, has evolved through the entire history of cosmic time since. It has likely merged with other galaxies, formed billions of stars, developed spiral structure, created planets, and possibly harbored life. Or it might have been destroyed in collisions, quenched of star formation, or disrupted by interactions. We cannot know. We see only its infancy, frozen in photons that travelled for cosmic ages to reach us. This temporal layering means the universe we observe is already dead, not in the sense of non-existence, but in the sense that nothing we see exists in the observed state anymore. Every star, galaxy, and structure has evolved beyond what we perceive. The night sky is a museum of extinct forms, images preserved in flight, travelling through space, reaching us long after their sources have changed or vanished. We observe ghosts. The photons are real, the energy is real, but the objects they represent are historical artifacts. Astronomy is archaeology. We excavate the past using light as our fossil record, reconstructing what was but cannot observe what is. The Hubble Deep Field, one of astronomy's most famous images, illustrates this dramatically. Taken in 1995, by pointing the Hubble Space Telescope at a seemingly empty patch of sky for 10 days, the image revealed approximately 3,000 galaxies in a region smaller than a grain of sand held at arm's length. Each galaxy appears as it existed billions of years ago, some from when the universe was less than 1 billion years old. These galaxies are ancestral forms, early-stage galaxies before they evolved into the mature ellipticals and spirals we see in the nearby universe. The galaxies in their current states are unknowable to us, hidden by the finite speed of light. What we see is what was, not what is. This disconnect creates a strange situation where the observable universe is perpetually obsolete. Every observation we make, every photon we detect, every piece of information we gather about cosmic structures comes from the past. The more distant the object, the more ancient the information. We cannot observe the present cosmos. We can only observe its history, stratified by distance into temporal layers, extending from 8 minutes ago for the Sun to nearly 13.8 billion years ago for the most distant observable objects. The present universe, the universe as it exists right now, in all locations simultaneously, is forever hidden from us by light speed's finite value and the relativity of simultaneity. Moreover, many stars we observe have already died in their own reference frames, even though we still see them shining. Massive stars with lifespans of only a few million years burn bright but brief. Any massive star farther than a few million light years, whose light we currently observe, might have already exhausted its fuel and exploded. The photons are still in transit, carrying images of a living star, but the star itself is gone, replaced by a neutron star, black hole, or dispersed remnant. We literally observe dead stars shining, their corpse light illuminating the night. When we finally observe their explosions in some distant future, it will be ancient news, an event that occurred long ago, finally announced by photons that took eons to deliver the message. The cosmos is a vast graveyard where we commune with the dead through ancient light, mistaking ghosts for living presences, because we cannot see beyond photons' illusions. The universe's slow death has begun. The universe's death is not a future event, but an ongoing process that began immediately after the Big Bang. The second law of thermodynamics guarantees that entropy disorder increases irreversibly in closed systems. The universe as a whole is a closed system with no external environment to exchange energy with. Therefore, cosmic entropy must increase monotonically from the Big Bang's low entropy initial state toward maximum entropy heat death. Every star that ignites, every chemical reaction that proceeds, every thought that forms, every particle that moves, increases entropy. The march toward death started 13.8 billion years ago and has continued unabated ever since. We exist during the dying process, mistaking temporary complexity for life, when in reality we inhabit a universe already well into its terminal decline. The Big Bang itself represented maximum cosmic vitality conditions farthest from equilibrium death. In the first moments after the Big Bang, the universe existed in an extraordinarily hot, dense, uniform state, far from thermal equilibrium. Temperatures exceeded trillions of degrees. Matter and energy existed as quark-gluon plasma and pure radiation. This represented minimum entropy, not because the state was orderly, but because the universe was small. Entropy scales with volume and particle number. The early universe's entropy was low simply because little space existed to contain disorder. As the universe expanded, cooling and diluting, entropy increased. Protons and neutrons formed from quarks. Nuclei assembled from nucleons. Atoms formed from nuclei and electrons. Each step represented increasing entropy as energy dispersed more widely and more states became accessible. The formation of stars and galaxies might seem to decrease entropy by creating structure from homogeneous gas. But this local entropy decrease is vastly outweighed by entropy increases elsewhere. When gas clouds collapse to form stars, gravitational potential energy converts to heat and radiation. The radiation carries entropy into space. Nuclear fusion in stellar cores produces entropy through randomizing photons and neutrinos. The net entropy change from star formation is strongly positive. Stars are entropy engines, converting ordered nuclear fuel into disordered radiation. Every star that shines increases cosmic entropy. The universe's 10 to the 24th stars collectively produce enormous entropy, far exceeding the local ordering represented by stellar structure itself. Life similarly increases entropy despite appearing to be ordered complexity. Living organisms maintain their internal order by consuming free energy from their environment and releasing waste heat. A human body consumes roughly 2,000 food calories per day and radiates approximately 100 watts of heat. Over a lifetime, each person increases environmental entropy far more than their body's structural order decreases entropy. The same applies to all life. Ecosystems, biospheres, and civilizations are temporary islands of complexity maintained by continually increasing surrounding entropy. When life eventually goes extinct, as all life must when stars fade and planets cool, the local ordering will vanish, while the entropy increase persists. Life represents a brief flourish of complexity during the long entropic decline from Big Bang to heat death. The current cosmic epoch, sometimes called the Stelliferous Era because it is dominated by stars, represents peak complexity but also marks the universe's middle age. Stars formed abundantly beginning a few 100 million years after the Big Bang as initial gas clouds collapsed. Star formation peaked approximately 10 billion years ago and has been declining since. The universe currently produces fewer new stars than in the past because available gas is being exhausted and dispersed. In the future, star formation will continue declining until it ceases entirely in approximately 100 trillion years, when all gas has been consumed or dispersed beyond gravitational reach. The Stelliferous Era lasts perhaps 100 trillion years total, from a few 100 million years after the Big Bang until 100 trillion years hence. We exist roughly 14 billion years into this era, having already passed peak star formation. The universe's stellar prime has ended. We live in its declining phase. After the Stelliferous Era comes the Degenerate Era, lasting from approximately 10 to the 14th years to 10 to the 40th years. During this era, no stars shine. The universe contains only stellar remnants, white dwarfs, neutron stars, black holes slowly cooling toward background temperature. Brown dwarfs and planets drift through darkness. Galaxies evaporate as stars scatter through gravitational interactions. The universe grows colder, darker, emptier. This represents advanced aging, closer to death than to birth. Structure persists, but no longer evolves interestingly. Complexity declines as gradients flatten and energy disperses. If protons decay, the degenerate era gives way to the black hole era around 10 to the 40th years, when even matter disintegrates. Black holes become the only significant repositories of mass and energy. They evaporate through Hawking radiation over timescales reaching 10 to the 100th years, releasing their contents as radiation. After the last black holes evaporate, the universe enters the dark era, where only a dilute bath of photons, neutrinos, and possibly electrons persists at temperatures approaching absolute zero. Entropy is at or near maximum. Heat death has arrived. The universe exists, but nothing happens. Time loses meaning. Death is complete. This progression from Big Bang vitality through stelliferous complexity to degenerate simplicity to dark erasure represents a dying process extending across incomprehensible time. We exist early in this process, only 13.8 billion years from birth. But the process is irreversible. Entropy cannot decrease. Death cannot be avoided. The universe has been dying since its first instant, and we are merely living during the brief interval when dying produces interesting complexity. In a meaningful sense, the universe is already dead because its fate is sealed, its trajectory determined, its ending inevitable. We watch a corpse cool, mistaking residual warmth for life, peak complexity already past. The universe might have already reached and passed its point of maximum complexity, meaning that the most interesting and intricate structures that will ever exist may already exist or have already existed. Future cosmic evolution will likely not produce greater complexity than current or past structures instead. Complexity will decline as stars fade, galaxies disperse, and entropy continues its inexorable increase towards simplicity. This suggests we live not in the universe's youth or maturity, but in its twilight past peak vitality, coasting on momentum toward eventual stagnation. The universe's most creative and fertile period has ended. What follows is slow unwinding and simplification. Complexity in this context means the number of distinguishable states, the information content, the diversity of structures, and the richness of processes occurring. The early universe immediately after the Big Bang was simple. Despite being hot and energetic, it consisted of uniform quark-gluon plasma with little differentiation. As the universe expanded and cooled, complexity increased. Protons, neutrons, and electrons formed. Light elements assembled through Big Bang nucleosynthesis. Atoms formed at recombination. Gravity amplified tiny density fluctuations into vast cosmic web structure. Galaxies condensed. Stars ignited. Heavy elements formed in stellar cores and supernovae. Planets coalesced. Chemistry became possible. Life emerged. Intelligence arose. Each step represented increasing complexity as more types of structures existed in more diverse arrangements. But this increase cannot continue forever. Thermodynamics sets limits. The second law requires entropy to increase, and maximum entropy corresponds to minimum complexity, a uniform featureless equilibrium. The universe must eventually transition from its current complex state to simple heat death. The question is whether that transition has already begun, and whether the maximum complexity has already been reached. Several lines of evidence suggest it has. Star formation, the process creating the most luminous and energetically active structures, peaked approximately 10 billion years ago, when the universe was roughly 3.8 billion years old. Observations of distant galaxies at various redshifts allow astronomers to reconstruct the cosmic star formation rate across time. The rate increased rapidly in the first few billion years, peaked around redshift 2, corresponding to 10 billion years ago, and has been declining ever since. Current star formation rates are roughly 1/10 the peak rate. Projections suggest star formation will continue declining, ultimately ceasing within 100 trillion years. We live long after peak stellar activity. The universe is no longer in its generative prime, but in its fading phase. Galaxy formation and merger activity also peaked in the past. The universe today contains large, mature galaxies that have undergone most of their growth and merging. Future mergers will occur, but less frequently, as cosmic expansion separates galaxies beyond gravitational interaction range. The spectacular collisions that create bursts of star formation and reshape galactic morphology were more common billions of years ago than now. The universe's structural evolution is winding down. It has already created its largest and most massive structures. Future changes will mostly involve dissolution and dispersal rather than construction. The emergence of life and intelligence represents perhaps the highest expression of cosmic complexity. Life concentrates information, maintains far from equilibrium conditions, and exhibits behaviors unpredictable from mere physics and chemistry. Intelligence compounds this through consciousness, language, technology, and culture. But life requires specific conditions, stable stars, planets in habitable zones, sufficient heavy elements for chemistry, protection from sterilizing radiation. These conditions were not available in the early universe, when only hydrogen and helium existed. They became common only after generations of stars synthesized heavy elements and scattered them through supernovae. Life on Earth emerged approximately 3.8 billion years ago, in the cosmic era when conditions became suitable. Life might be more common now than in the past, simply because required conditions took billions of years to develop. However, life's future prospects are grim. As stars exhaust their fuel over coming trillions of years, habitable conditions will become rarer. Eventually, no new stars form, no planets reach habitable temperatures, and no environments support biology. Existing life will go extinct as stars fade and planets freeze. Intelligence will disappear as civilizations fail without energy sources. The brief flourish of biological complexity will end, never to recur. If intelligence arose multiple times across cosmic history, the combined total intelligence peaked at some point and will decline thereafter. We might exist near that peak or past it, meaning the universe will never again see complexity matching current biological and cognitive richness. Black holes represent growing complexity. In one sense, they contain enormous entropy and information. As more matter falls into black holes over cosmic time, their entropy increases. Supermassive black holes at galactic centers will eventually consume most stars and material in their galaxies. By the black hole era, black holes will dominate the universe's mass and entropy content. However, black hole complexity is hidden behind event horizons, inaccessible to external observation. When black holes evaporate through Hawking radiation, their entropy disperses as featureless thermal radiation. The final state dilute radiation, at near absolute zero, is simpler than current cosmic structure. Total entropy increases, but complexity decreases. If peak complexity has passed, then the most interesting era of cosmic history is behind us. The universe has already created its richest tapestry of stars, galaxies, planets, chemistry, and life. Future evolution leads away from this richness toward growing simplicity and emptiness. We exist during the sunset of cosmic creativity, watching structures formed in more vital times slowly decay and disperse. In this sense, the universe is already dying past its prime, losing complexity, simplifying toward eventual featureless equilibrium. The fact that processes continue and structures persist should not blind us to the directionality of change. Complexity is declining. Richness is fading. The universe is dying, and peak vitality lies in the past, not the future. Stars dying faster than forming. The universe's stellar population is in terminal decline. Star formation, the process creating luminous energy sources that power galaxies and enable planetary systems, peaked approximately 10 billion years ago when the universe was merely 3.8 billion years old. Since that peak, the cosmic star formation rate has decreased steadily and continues falling. Current star formation rates are roughly 1/10 of peak rates. Projections based on available gas supplies and cosmic expansion suggest star formation will continue declining over coming billions of years, ultimately ceasing entirely within approximately 100 trillion years, when all available hydrogen and helium have been exhausted or dispersed beyond gravitational reach. The universe is running out of fuel for new stars, while existing stars continue dying. The stellar life cycle operates on timescales ranging from millions to trillions of years, depending on mass. Massive stars with tens of solar masses burn brilliantly but briefly, exhausting their fuel in mere millions of years before exploding as supernovae. Mid-sized stars like the Sun shine for billions of years. The Sun will last approximately 10 billion years total, having already consumed half its hydrogen fuel. Low-mass red dwarf stars, with 1/10 the Sun's mass burn, so slowly they can persist for trillions of years. The longest-lived red dwarfs will outlast all other stellar types, continuing to shine long after massive and solar-type stars have gone extinct. Currently, the universe contains approximately 10 to the 24th stars, a trillion. These stars span all evolutionary stages, from newborn protostars, still condensing from gas clouds, to ancient red giants nearing death, to white dwarf corpses cooling toward darkness. Each second, stars die throughout the universe as they exhaust fuel and collapse into white dwarfs, neutron stars, or black holes. Simultaneously, new stars ignite as gas clouds collapse and nuclear fusion ignites in their cores, For billions of years, the birth and death rates roughly balanced, maintaining stable stellar populations. But this balance has shifted. Deaths now exceed births because the star formation rate has declined, while the death rate continues as stars formed billions of years ago reach their lifespan's ends. The decline in star formation results from multiple factors. First, available gas is being consumed. Stars form from hydrogen and helium gas in molecular clouds. As stars form, they convert this gas into stellar material locked inside stars or blown away in stellar winds and supernovae. Some gas is recycled when dying stars eject material, but not all some remains locked in stellar remnants, like white dwarfs, or falls into black holes. The net effect is gradual depletion of available gas for new star formation. Second, cosmic expansion disperses gas. As space expands, gas clouds in the intergalactic medium spread over larger volumes, decreasing density below thresholds required for gravitational collapse. Third, feedback from previous star formation inhibits new formation. Supernovae, stellar winds, and radiation from massive stars heat surrounding gas and blow it out of galaxies, reducing available material for new stars. Observations confirm the declining star formation rate across cosmic history. Astronomers study distant galaxies at various redshifts to reconstruct star formation rates at different cosmic epochs. High redshift galaxies seen as they existed billions of years ago show vigorous star formation with rates hundreds of times current Milky Way rates. These galaxies appear blue from hot young stars and show strong emission lines from ionized hydrogen surrounding star-forming regions. Lower redshift galaxies closer in time show reduced star formation rates. Local nearby galaxies today show minimal star formation compared to their ancient counterparts. The Milky Way currently forms approximately 2 solar masses worth of new stars per year, modest compared to past rates. The consequences of declining star formation are profound. Stars provide the energy sources that make galaxies luminous, drive chemical evolution through nucleosynthesis, and create planetary systems potentially harboring life. As star formation declines, fewer new energy sources ignite. Galaxies will gradually dim as their stellar populations age. Within 100 trillion years, no new stars will form anywhere in the universe. The stelliferous era, the epoch dominated by shining stars, will end. What follows is the degenerate era where only stellar remnants persist: white dwarfs, neutron stars, brown dwarfs, and black holes. These objects emit little light and cool slowly toward background temperature. The universe will transition from brilliant stellar luminosity to near total darkness. Some existing stars will continue shining for extraordinary durations. Red dwarfs formed today, or in the near future, will burn for trillions of years, outlasting all other stellar types. The last red dwarf stars will flicker out perhaps 100 trillion years hence, marking the final deaths of natural fusion-powered luminous objects. After that, no stellar fusion occurs anywhere. Any remaining light comes from cooling white dwarfs, radiating residual heat, or from matter accreting onto black holes. Over timescales of 10 to the 20th years, even white dwarfs cool to near absolute zero, becoming black dwarfs, dark, cold stellar corpses drifting through space. The universe is dying in the sense that its stellar vitality is waning irreversibly. The peak of stellar activity lies billions of years in the past. We live in an aging cosmos past its prime, watching the last great generation of stars illuminate the darkness while knowing no comparable generation will follow. Stars are dying faster than forming, and this imbalance will only worsen. The universe's fuel is running out, its fires are dimming, and the approaching darkness is inevitable. In cosmically meaningful terms, the universe is already in its terminal phase, past peak energy output, past peak luminosity, coasting on momentum toward eventual stillness and cold. The vibrant stellar cosmos we observe represents the final flourish of a dying universe, spending down its dwindling capital of free energy and available gas. The cosmic web stretching apart. The cosmic web, the largest scale structure in the universe, consisting of galaxy clusters, filaments, walls, and voids, is being torn apart by accelerating cosmic expansion driven by dark energy. This vast scaffolding of matter that spans billions of light years formed through gravitational clustering over cosmic history as matter clumped into increasingly large structures. But dark energy opposes this clustering. As dark energy becomes increasingly dominant, it counteracts gravity on cosmological scales, preventing new structure formation and eventually disrupting existing structures. The cosmic web is being stretched, thinned, and ultimately dissolved by relentless expansion that will not stop or reverse. The cosmic web's formation began with tiny density fluctuations in the early universe, imprinted during cosmic inflation and visible in the cosmic microwave background radiation. These fluctuations regions, slightly denser or less dense than average by parts per million, grew over billions of years through gravitational instability. Denser regions attracted surrounding matter, becoming denser still in a runaway process. Lower density regions lost matter to denser neighbors, becoming voids. The result is the cosmic web we observe today. Galaxies concentrated along filaments and sheets surrounding vast empty voids, with dense galaxy clusters at filament intersection. But this structure-building process has been opposed by cosmic expansion since the Big Bang. Expansion works to dilute matter and reduce clustering. During the matter-dominated era from approximately 50,000 years after the Big Bang until 5 billion years ago, matter's gravitational attraction dominated over expansion on scales below approximately 100 million light-years. Structures could form and grow despite expansion because gravity on these scales overcame expansion's dispersing effect. Galaxy clusters, the largest gravitationally bound structures, assembled during this era through mergers of smaller groups and continuous infall of surrounding matter. Approximately 5 billion years ago, dark energy became dominant as matter diluted with expansion, while dark energy's density remained constant. This transition fundamentally changed cosmic structure evolution. Dark energy produces gravitational repulsion, effectively anti-gravity, that drives accelerating expansion. On scales larger than approximately 100 million light-years, dark energy's repulsion now exceeds gravity's attraction. This prevents new large-scale structure formation. Galaxy clusters will not grow significantly larger. Superclusters, loose associations of multiple clusters, will not collapse into gravitationally bound systems. The cosmic web has stopped growing and begun dissolving. The dissolution proceeds slowly but inexorably. Galaxy clusters remain gravitationally bound because their internal densities are high enough that gravity dominates dark energy. But clusters lose their surrounding material, the diffuse gas, and loosely bound galaxies in their outskirts to expansion. Filaments connecting clusters thin as expansion stretches them. Over billions of years, the cosmic web's contrast diminishes. Dense regions remain dense but do not grow denser. Voids expand and become emptier. The distinction between structures and voids gradually fades as expansion dominates increasingly. On timescales of hundreds of billions of years, even galaxy clusters begin evaporating. While clusters remain gravitationally bound, individual galaxies within clusters have velocities that sometimes exceed cluster escape velocity. Random gravitational encounters between galaxies can accelerate some members above escape velocity, causing them to leave the cluster and drift into expanding voids. This process, called evaporation, slowly disperses clusters over timescales of 10 to the 19th to 10 to the 20th years. Most galaxies in a cluster eventually scatter, leaving only the densest core. Individual galaxies' gravity is too weak to bind them together in loose associations. Like clusters, they gradually separate as expansion carries them apart. The ultimate fate is cosmic isolation. Within a few 100 billion years, accelerating expansion will have placed all galaxies, except those in the local group the Milky Way, Andromeda, and their satellites gravitationally bound together beyond the cosmic event horizon. These galaxies will have vanished from observability, having receded beyond the distance where light can ever reach us. The cosmic web, as a large-scale structure spanning the observable universe, will have disappeared. What remains observable will be only the merged remnant of the local group, floating alone in darkness, surrounded by empty, expanding space. The cosmic web's dissolution represents the universe dying in a structural sense. The largest structures ever assembled are being unmade by expansion. What took billions of years to build through gravitational assembly is being erased over billions more years through dark energy's inexorable dispersal. The universe is not merely failing to create new structures, it is actively destroying existing ones, working backward from the largest scales down towards smaller ones. Eventually, even galaxies will disperse. As their stars scatter through random gravitational interactions, the web will be gone, the clusters will be gone, and only isolated stellar remnants will drift through the expanding void. The universe is already in this terminal phase, the web is already dissolving, the clusters already losing material, the isolation already advancing. We observe a structure in the late stages of disassembly, watching cosmic architecture that peaked billions of years ago slowly collapse into scattered debris. Entropy, irreversible march to disorder. Entropy measures disorder, or the number of possible microscopic arrangements consistent with a system's macroscopic properties. The second law of thermodynamics states that in any closed system, entropy never decreases, it either increases or remains constant in perfectly reversible processes. The universe as a whole constitutes a closed system with no external environment to exchange energy with. Therefore, cosmic entropy must increase monotonically from the Big Bang's low entropy initial state toward maximum entropy heat death. Every process that occurs, every star that burns, every black hole that forms, every thought that thinks increases total entropy. This increase is irreversible. Entropy cannot spontaneously decrease. The universe marches one direction only, from order toward disorder, from structure toward uniformity, from complexity toward simplicity. The early universe began in a peculiar state, extraordinarily hot and dense, but also remarkably uniform and low entropy. This seems paradoxical. How can a high-temperature plasma be low entropy? The answer lies in the universe's small size. Entropy scales with volume and particle number. The early universe, despite being hot, was tiny, all matter and energy compressed into a small region. The number of possible microstates was limited by the small volume. As the universe expanded, volume increased exponentially, creating vast numbers of new possible microstates. Entropy increased as matter and energy dispersed into this expanding space. Expansion itself drives entropy increase. Structure formation further increases entropy despite appearing to create order. When gas clouds collapse to form stars, they release gravitational potential energy as heat and radiation. This radiation carries entropy into space, far more entropy than the decrease represented by the star's organized structure. Stars are entropy generators. Nuclear fusion produces entropy by converting ordered nuclear fuel into disordered radiation and neutrinos. Every photon emitted by every star increases cosmic entropy. The Sun alone produces approximately 10 to the 27th watts of power, converting 4 million tons of matter into energy every second. This energy radiates into space as photons that redshift and disperse, increasing entropy perpetually. Black holes represent the ultimate entropy repositories. Bekenstein and Hawking demonstrated that black hole entropy is proportional to event horizon area, measured in Planck units. A solar mass black hole contains entropy of approximately 10 to the 54th in fundamental units. Supermassive black holes with billions of solar masses hold entropy exceeding 10 to the 77th. When matter falls into black holes, cosmic entropy increases dramatically. The matter's information becomes encoded on the horizon in a maximally entropic configuration. Currently, supermassive black holes at galactic centers contain significant entropy. As more matter falls into black holes over cosmic time, entropy stored in black holes will dominate all other sources. When black holes evaporate through Hawking radiation, entropy continues increasing. The radiation emitted is thermal maximally disordered. The entropy of emitted radiation exceeds the black hole's entropy, ensuring total entropy increases even as the black hole shrinks. After all black holes evaporate, their entropy content will have been converted to dispersed thermal radiation filling space. This radiation continues redshifting and diluting as expansion proceeds, but entropy never decreases. The universe approaches maximum entropy asymptotically. Maximum entropy corresponds to thermal equilibrium, all energy uniformly distributed at the same temperature, with no gradients to drive processes. In this state, often called heat death, entropy can increase no further because the universe has reached the most disordered configuration possible given its energy content. No structure persists, no processes occur. The universe exists in a changeless state of perfect disorder. Time becomes meaningless because no events mark its passage. This represents the universe's final death, not annihilation, but eternal stagnation. The irreversibility of entropy increase means the universe cannot return to earlier low entropy states. We cannot rewind cosmic evolution. Scattered ashes do not spontaneously reassemble into trees. Dispersed radiation does not reconcentrate into stars. The universe cannot reverse its trajectory from disorder back to order. The ending is as inevitable as the beginning was unrepeatable. Every moment that passes increases entropy. Every process that occurs drives the universe closer to heat death. The march is inexorable, the destination certain, the timeline just a matter of waiting. In this sense, the universe is already dying and has been dying since the Big Bang. The initial low entropy state represented peak vitality and order. Every subsequent moment represents decline toward maximum entropy disorder. We exist partway through this decline, in an era where entropy has increased substantially but not yet maximized. The universe is not at heat death yet, but it is dying. Entropy is increasing, gradients are flattening, free energy is dissipating. The second law guarantees this process continues irreversibly until entropy maximizes and death is complete. The universe is not alive in any meaningful thermodynamic sense. It is a dying system running down toward equilibrium, and nothing can stop or reverse this process. Physics permits only one direction, toward increasing entropy and approaching death. The heat death already approaching. Heat death represents the universe's thermodynamic endpoint, a state of maximum entropy where all energy exists at uniform temperature with no gradients remaining to drive processes. In this final state, stars have long since exhausted their fuel, black holes have evaporated, matter has decayed or dispersed, and only dilute radiation at temperatures approaching absolute zero fills expanding space. No work can be extracted because everything sits at equilibrium. No structures can form or persist because no energy differentials exist to build or maintain them. The universe becomes a featureless void, not destroyed, but rendered eternally inert and changeless. While heat death lies trillions upon trillions of years in the future, the approach toward it has already begun and proceeds inevitably. Every process occurring in the universe moves entropy closer to maximum. Every star that burns converts organized nuclear fuel into disordered radiation, increasing entropy. Every photon that scatters increases entropy. Every particle collision increases entropy. The sum of all these processes drives relentless entropic increase. We are not heading toward heat death, we are already on the path, already in motion toward that final state, with no mechanism to reverse direction or halt progress. The timeline toward heat death proceeds through predictable stages. Currently, we inhabit the stelliferous era, the epoch of shining stars. This era began a few 100 million years after the Big Bang, when first stars ignited, and will end approximately 100 trillion years from now, when the last stars exhaust their fuel. We are roughly 14 billion years into this era, having passed peak star formation about 10 billion years ago. The stelliferous era represents the universe's most active and complex phase, but it constitutes only a tiny fraction of total cosmic time. If we compress cosmic history into a single year, the stelliferous era lasts mere hours at the beginning. The vast majority of time lies in subsequent darker, colder, emptier epochs. After the stelliferous era comes the degenerate era, lasting from approximately 10 to the 14th years to 10 to the 40th years. No stars shine during this epoch. The universe contains only stellar remnants, white dwarfs, neutron stars, brown dwarfs, and black holes slowly cooling toward background temperature. Galaxies have evaporated, scattering stars and remnants through expanding voids. The universe grows darker and colder as remaining objects radiate away their residual heat into space that continues expanding and diluting all energy. This era is characterized by gradual cooling, and dispersal structures persist but slowly fade toward invisibility. If protons decay, as some grand unified theories predict, the degenerate era gives way to the black hole era around 10 to the 40th years. Proton decay disintegrates remaining matter planets, brown dwarfs, stellar remnants into electrons, positrons, neutrinos, and photons. Electrons and positrons annihilate, producing gamma rays that redshift with cosmic expansion. Black holes become the only significant mass concentration. They evaporate through Hawking radiation over timescales reaching 10 to the 100th years for supermassive black holes. A solar mass black hole evaporates in approximately 10 to the 67th years. Larger black holes persist longer, scaling as mass cubed. After the last black holes evaporate around 10 to the 100th years, the universe enters the dark era, the final epoch, approaching heat death. Only an extraordinarily dilute bath of photons, neutrinos, and possibly electrons persists at temperatures near absolute zero. The cosmic microwave background radiation, currently at 2.7 Kelvin, will have cooled to temperatures measured in 10 to the negative 30th Kelvin or lower. Photon wavelengths exceed light years. Particle densities fall to perhaps 1 particle per cubic light year or less. The universe exists in near-perfect equilibrium, approaching maximum entropy asymptotically over infinite time. Entropy continues increasing, even in the dark era, through rare quantum fluctuations, but increases become negligible as the universe approaches maximum entropy. The final state is not precisely maximum entropy, but asymptotically approaches it. The universe never quite reaches perfect equilibrium, but gets arbitrarily close. Temperature approaches but never quite reaches absolute zero due to quantum effects and dark energy's persistence. Time continues in the mathematical sense, but loses operational meaning because nothing changes measurably. The universe exists in eternal stasis. This entire trajectory from stelliferous complexity to dark simplicity was set in motion at the Big Bang. The initial conditions and physical laws determine the path. No surprises alter the destination. The universe is not heading somewhere uncertain. It is following rails laid down 13.8 billion years ago, leading inexorably to heat death. We are merely passengers on this train, experiencing the journey through successive epochs, but unable to alter the route or destination. The universe is already dying because it has been dying since birth, and heat death is not a future threat, but the certain conclusion of a process already in progress. The approach is gradual, spanning timescales that dwarf comprehension, but it is happening now and has been happening throughout cosmic history. Heat death is not coming. We are already going toward it with every passing second. Time may be an illusion. Time appears to flow from past to future. We experience moments in sequence, remember what was, anticipate what will be, and perceive ourselves moving through time at 1 second per second. But physics suggests this intuitive picture might be profoundly wrong. Time's flow might be an illusion created by consciousness rather than an objective feature of reality. According to some interpretations of relativity and quantum mechanics, all moments exist simultaneously in an eternal, four-dimensional space-time structure. Past, present, and future are equally real, but inaccessible from one another. Our sense of moving through time, of present moments being special, of the future being open, and the past fixed, these might be psychological constructs rather than physical truths. Albert Einstein's relativity theory fundamentally changed our understanding of time. Special relativity demonstrated that simultaneity is relative events that appear simultaneous in one reference frame occur at different times in another frame, moving relative to the first. There is no universal now spanning the universe. The present moment is observer-dependent. This already challenges the notion of time flowing uniformly for everyone. General relativity goes further, showing that time dilates in gravitational fields, and that space-time itself can curve, stretch, and warp. Time is not a fixed background against which events occur, but a flexible dimension intertwined with space. The block universe interpretation takes these insights to their logical conclusion. If relativity is correct, and there is no universal present, then all moments in time must exist equally. The universe is not a three-dimensional space evolving through time, but a four-dimensional space-time block containing all events, past, present, and future, simultaneously. Your birth, your current reading of these words, and your eventual death all exist as events in the space-time block. From an external perspective outside the block, if such a perspective makes sense, the entire history from Big Bang to heat death exists statically as a complete structure. Nothing moves or changes. Change is an illusion created by consciousness experiencing time slices sequentially. This view radically reinterprets what it means for the universe to be alive or dead. If all moments exist simultaneously, the universe does not evolve from living to dead. It simply exists as a four-dimensional structure containing regions we label as early, middle, and late. The Big Bang and heat death are just different locations in the block, beginning and end only from temporal perspectives within the block. From outside, there is no beginning or end, no birth or death, no evolution or change. The universe is eternal and static. Time's flow is something conscious observers experience as they process information along their world lines, but it is not a fundamental feature of reality. Evidence for the block universe comes from relativity's successful predictions. The theory has passed every experimental test with extraordinary precision. GPS satellites require relativistic corrections for time dilation. Gravitational waves detected by LIGO match general relativity's predictions exactly. Black holes behave as Einstein's equations predict. If relativity is correct, and it appears to be then the block universe interpretation follows naturally. The alternative is to maintain that some frames present is objectively special, while others are not. But this seems arbitrary and contradicts relativity's principle that all inertial frames are equivalent. However, the block universe creates puzzles. If the future already exists, is free will an illusion? If all events are predetermined by the space-time structure, do we have no genuine choices? Compatibilist philosophers argue free will and determinism can coexist even if the future exists. We do not know it, and our decisions are still meaningfully ours. Others embrace hard determinism, accepting that free will is indeed illusory. The block universe also challenges notions of causality. If past and future both exist, why does causation run from past to future? The answer might lie in entropy's direction. The arrow of time is thermodynamic, defined by entropy increase, not by metaphysical flow. The psychological impact of accepting the block universe is profound. It means everything that will happen to you has already happened in the eternal space-time structure. Your future is as fixed as your past. Death is not an ending, but a region of the block beyond your world line's termination point. From this perspective, asking if the universe is dead is like asking if a mountain is already climbed. The mountain exists with all elevations simultaneously. Climbing is just traversing them sequentially from a particular path. The universe exists eternally with all its history. Living and dying are experiences of traversing that history, not objective states of the universe itself. If time is illusory and the block universe is real, then the universe cannot be dead because it cannot die. Death implies temporal change from living to dead, but the block does not change. It simply is. All moments exist eternally. The Big Bang is not past. It exists eternally at temporal location 0. Heat death is not future. It exists eternally at temporal location 10 to the 100th years. The present is not special. It is just the temporal location you currently experience. The universe is neither alive nor dead. It is timeless, eternal, unchanging, a four-dimensional sculpture in space-time that consciousness experiences sequentially, but that exists all at once from any perspective outside time. This might be the ultimate answer to whether the universe is already dead. The question itself presupposes a flow of time that might not exist. The universe may be beyond such distinctions, eternal and complete. Block universe, everything already exists. The block universe theory suggests that space-time is a static four-dimensional structure where all events past, present, and future exist simultaneously and eternally. Time does not flow. It simply is one of four dimensions in this structure. Our perception of moving through time, of the present being unique and the future open, arises from consciousness processing events sequentially along world lines through the block. But from an objective perspective, if such exists, the entire cosmic history from Big Bang to heat death is laid out complete and unchanging. Nothing becomes or ceases to be. Everything that ever existed exists now and will exist, already exists in the eternal space-time block. This view follows naturally from Einstein's general relativity. Relativity describes the universe as a four-dimensional pseudo-Riemannian manifold, where time is a coordinate similar to spatial coordinates, but with different mathematical properties. The laws of physics, Einstein's field equations, relate space-time curvature to matter and energy distribution, but do not specify that time flows or events unfold. The equations simply describe relationships between space-time geometry and its contents. Solutions to Einstein's equations represent entire space-time manifolds, not three-dimensional spaces evolving through time. The Schwarzschild solution describing black holes is a complete four-dimensional geometry containing the black hole's entire history. Nothing in the mathematics suggests time flows or events become real sequentially. The block universe resolves relativity's relativity of simultaneity problem. In special relativity, observers in different reference frames disagree about which events are simultaneous. What appears simultaneous for you occurs at different times for someone moving relative to you. This makes no sense. If only present events are real, it would mean reality itself is observer-dependent. But if all events are equally real, regardless of temporal location, then relativity of simultaneity is unproblematic. Different observers partition space-time into space and time differently, but all events exist independently of these partitions. The block universe provides an objective reality underlying relative simultaneity. In the block universe, causation becomes a structural feature rather than a dynamic process. One event causes another, not by producing it, but by being related to it through the space-time structure in ways constrained by light cones and physical laws. Your birth causes your current existence because these events are connected by your world line through the block, with information and energy flowing from earlier events to later ones. But both events exist eternally. Causation is the pattern of how events relate, not a process by which future events come into being from past events. The future does not become real through time's passage. It is already real, structured in particular ways determined by past events and physical laws. This interpretation profoundly affects how we understand the universe's state. If everything exists eternally in the block, asking whether the universe is dead now becomes meaningless. The universe does not have a state now. It has a complete four-dimensional structure containing all states at all times. The Big Bang, the Stelliferous Era, heat-death all exist simultaneously as regions of the block at different temporal coordinates. From a timeless perspective, the universe is not alive during the Stelliferous Era and dead during heat-death. It is a geometric structure containing both eras eternally. Life and death are properties of temporal regions, not of the universe as a whole. However, the block universe does not eliminate our experience of time or make thermodynamics irrelevant. We still experience time flowing because consciousness processes information sequentially. Memories form in one direction because entropy increases in that direction. Causation runs from past to future because of entropic arrow low entropy past, high entropy future. These features emerge from the block structure even though the block itself is static. The second law of thermodynamics becomes a statement about the block's geometry. Entropy values increase along time-like world lines from Big Bang region toward heat-death region. This creates the arrow of time we experience, even though all moments exist simultaneously. The block universe has radical implications for existence and meaning. If everything that will happen already exists, then future suffering and joy are already real, not merely potential. This might increase urgency to address suffering. It is not something that might occur, but something that exists eternally at future temporal locations and needs addressing. Alternatively, it might provide solace for lost loved ones who died, still exist at their temporal locations in the block, eternally experiencing their lives, even though those locations are inaccessible from our current position. Death does not erase them, but simply means we cannot interact with their space-time regions anymore. The block universe interpretation remains debated among physicists and philosophers. Some embrace it as the natural conclusion of relativity. Others reject it, arguing presentism only the present exists, or the growing block universe past and present exist, future does not yet. These alternatives face challenges explaining relativity of simultaneity. Quantum mechanics complicates matters further. Wave function collapse seems to involve genuinely indeterministic events, suggesting the future is not fixed. But many worlds' interpretation avoids collapse, maintaining determinism consistent with the block universe. The debate continues, with no consensus. If the block universe is correct, the question of whether the universe is already dead must be reframed. The universe is eternally what it is, containing both vibrant and dead regions, and the distinction between them is perspectival rather than absolute. Observations from a dying perspective. Every observation we make of the universe reveals a dying cosmos, not because we selectively notice death, but because death pervades everything we can observe. The light reaching our telescopes comes from stars that have already exhausted fuel and gone dark, from galaxies that have evolved beyond their observed states, from a cosmic microwave background that represents the universe's cooled remnant from its hot birth. We observe ancient light from objects in their primes that have since faded. We see energy gradients that are flattening. We measure entropy increases that cannot reverse. Every data point confirms the universe's dying has been dying throughout its history, and we are merely documenting the ongoing decline. Stellar observations reveal dying stars at every evolutionary stage. White dwarf stellar corpses, slowly cooling, outnumber main sequence stars in some regions. Planetary nebulae surround dying stars as they shed outer layers. Supernova remnants expand through space, marking where stars exploded. Red giants bloat before death. We observe more evidence of stellar death and decline than of stellar birth and vitality. Young star-forming regions exist, but they are outnumbered by regions where star formation has ceased. The ratio of dying to forming stars increases as the universe ages. Future observations will show even more death and less birth as star formation continues declining. Galaxy observations show systems past their prime. Most galaxies have exhausted their gas supplies and ceased significant star formation. Elliptical galaxies contain old red stars with minimal ongoing star formation. Even spiral galaxies, like the Milky Way, form stars at reduced rates compared to their past. Observations of high redshift galaxies show more vigorous activity billions of years ago, intense star formation, frequent mergers, abundant gas. Contemporary galaxies appear quiescent by comparison, having converted most available gas into stars or lost it to outflows. The universe's galactic population is aging, fading, and declining. The cosmic microwave background itself is evidence of death, or at least irreversible change, from a hot dense state toward cold emptiness. The CMB photons were emitted when the universe cooled from plasma to neutral atoms at 3000 Kelvin. These photons have been traveling for 8 billion years, cooling through cosmological redshift to current 2.7 Kelvin. They will continue cooling toward absolute zero as expansion proceeds. The CMB is not a sign of ongoing vitality, but a cooling ember from the universe's hot youth, exactly what we would expect from a system approaching heat death. Its temperature decreases inexorably. Its energy density dilutes with expansion. The CMB represents thermodynamic decay in action. Entropy measurements confirm irreversible increase. Every astrophysical process we observe increases total entropy. Stars burning increase entropy. Black holes forming increase entropy. Gas expanding into voids increases entropy. Structure formation increases entropy more than it decreases it locally. The overall cosmic entropy grows monotonically, exactly as the second law demands for a dying closed system. We have never observed entropy decrease anywhere except in local subsystems powered by larger entropy increases elsewhere. The universe's total entropy arrow points unambiguously toward heat death. Dark energy observations reveal accelerating expansion that will ultimately tear apart structures and isolate regions beyond observability. The universe is not merely expanding, but accelerating, driven by dark energy, comprising 68% of total energy density. This acceleration will cause galaxies to disappear beyond event horizons, the cosmic web to dissolve, and structure to disperse. We are observing a universe actively destroying its own complexity through runaway expansion. This is not birth or growth, but dissolution and death playing out on cosmic timescales. Even observations of nearby objects reveal decline. The Sun has burned half its hydrogen fuel and will exhaust the rest within 5 billion years. Earth's core cools gradually, slowly losing internal heat. The Moon drifts slowly away from Earth, extracting rotational energy. Everything we observe tends toward lower energy states, cooler temperatures, and greater disorder. Nothing we observe suggests renewal or rebirth. No mechanism appears that could reverse entropy, reignite stellar populations after they fade, or restore complexity after it dissipates. Every observation confirms the universe is terminal. Our observations come from a dying perspective because we are embedded in the dying universe, made of material, subject to the same laws, experiencing the same entropic flow. We cannot observe from outside or from a different era. We observe from here and now, 13.8 billion years, into a process that will continue for timescales exceeding comprehension. But 13.8 billion years is long enough to see clear trends. Star formation peaked and declined. Entropy increased irreversibly. Expansion accelerated. Structures matured and began dispersing. We observe a universe well into its decline from peak complexity toward terminal simplicity. Future observations will only confirm this trajectory more clearly. The universe may not be dead yet, but from our dying perspective, watching dying stars in a dying cosmos, death is not distant future, but present reality unfolding around us. The last star's countdown begun. The universe will eventually run out of stars, all stellar fusion will cease, and the cosmos will plunge into permanent darkness. This is not distant speculation, but inevitable consequence of finite gas supplies and irreversible entropy increase. Star formation requires hydrogen and helium gas in sufficient density to collapse gravitationally and ignite fusion. The universe's gas supply is finite and diminishing. Every star formed consumes gas. Every supernova disperses gas beyond gravitational reach. Cosmic expansion dilutes gas below collapse thresholds. The star formation rate has been declining for 10 billion years and will continue declining until it ceases entirely approximately 100 trillion years from now. The countdown to the last star has already begun. Currently, the universe contains approximately 10 to the 24th stars, a trillion. This represents the cumulative stellar population built up over 13.8 billion years of star formation. But the rate of new star formation has dropped to roughly 1/10 of its peak 10 billion years ago. The Milky Way forms approximately 2 solar masses worth of new stars per year, down from perhaps 10 to 20 solar masses per year at peak. Other galaxies show similar declines. The universe-wide star formation rate is falling and will continue falling as gas supplies deplete. Massive stars live briefly millions of years and have already gone through many generations since the Big Bang. The most massive stars today are not the original stars, but descendants of multiple previous generations. Each generation of massive stars consumes gas, fuses it to heavier elements, and returns some processed material through supernovae while locking other material in remnants. The net effect is gradual conversion of pristine hydrogen and helium into heavier elements and stellar remnants, reducing available material for future star formation. Low-mass stars live extraordinarily long. Red dwarfs with 1/10 the Sun's mass can burn for trillions of years. A red dwarf forming today will outlive the Sun by factors of hundreds. These long-lived stars will be the last natural fusion sources in the universe. The final generation of red dwarfs forming in the far future, when gas supplies are nearly exhausted, will burn their fuel slowly over trillions of years, providing the universe's last starlight before darkness becomes permanent. The very last star to exhaust its fuel and fade perhaps 100 trillion years from now will mark the end of the stelliferous era. After stars cease forming, the existing stellar population gradually dies. Solar-type stars like the Sun will become red giants, then shed their envelopes to form white dwarfs over the next few billion to trillion years. More massive stars explode as supernovae. Low-mass stars burn slowly but eventually exhaust fuel. Within 100 trillion years, all hydrogen-burning main sequence stars will have died. What remains are stellar remnants, white dwarfs, neutron stars, black holes, and the longest-lived red dwarfs still burning dimly. These final red dwarfs provide the universe's last natural light. They burn so slowly that a single red dwarf could outlast the combined lifetimes of millions of solar-type stars. As these final stars age, the universe grows progressively darker. Fewer and fewer fusion sources remain active. The average luminosity per unit volume decreases exponentially. Eventually, perhaps around 100 trillion years from now, the last red dwarf exhausts its hydrogen, fusion ceases, and the star contracts into a cooling white dwarf or similar remnant. At this moment, the stelliferous era ends. No fusion occurs anywhere in the universe. The age of stars is over. What follows is the degenerate era, an age of darkness, populated only by cooling stellar remnants. White dwarfs slowly radiate residual heat, cooling over timescales of 10 to the 20th years toward black dwarf state, crystallized stellar corpses at near absolute zero. Neutron stars similarly cool, though more slowly due to their compact size. Brown dwarfs failed stars, lacking sufficient mass to ignite hydrogen fusion cool from their formation temperatures toward darkness. Black holes persist, growing by accreting stray material, but emitting only faint Hawking radiation. The universe becomes a cold, dark cemetery of stellar remnants drifting through expanding voids. This countdown is irrevocable. No mechanism can create new gas supplies once existing gas is consumed or dispersed. No process can restart star formation after gas is exhausted. The universe has one stellar epoch, and we are living near its middle past peak formation, headed toward extinction. In a meaningful sense, the countdown to the last star represents the universe's terminal phase. Once the last star dies, no comparable energy sources will ever exist again. Stellar populations are not renewable. The stelliferous era is a one-time event in cosmic history, and its end is approaching just as surely as its beginning occurred. We exist during the declining phase of the only era when stars will shine. The universe will spend 99.9% of its existence in darkness. After the last star fades, a darkness we are already sliding toward as star formation declines and existing stars burn down toward extinction. Determinism, the future already written. The universe might be dead, in the sense that its entire future is already determined, not merely predictable, but absolutely fixed by initial conditions and physical laws. If determinism is true, then everything that will happen is merely the unfolding of what must happen given how things began. The future exists as inevitably as the past exists historically. Your choices tomorrow are already determined by brain states today, which were determined by yesterday's states, tracing back through causal chains to the Big Bang's initial conditions. Nothing could be different. The appearance of possibility and choice is illusion. The universe is not alive with genuine openness and potential, but dead, its entire trajectory already written, just waiting to be experienced by beings who mistakenly believe they have free will. Classical physics is fundamentally deterministic. Newton's laws completely determine a system's future evolution, given initial positions and velocities. If you know every particle's state at one moment and all forces acting, you can calculate precisely where every particle will be at any future moment. The universe operates like clockwork, wound up at the Big Bang, ticking forward according to fixed rules, executing a program already implicit in initial conditions. Pierre-Simon Laplace famously imagined a demon knowing all particle positions and momenta, who could compute the entire future and past. Such a demon would see the universe's complete history laid out deterministically from Big Bang to heat death, with no genuine uncertainty or freedom anywhere. General relativity maintains determinism. Einstein's field equations relate space-time curvature to matter-energy distribution. Given initial conditions on a spatial slice, the geometry and matter distribution at one moment, the field equations determine the geometry and matter distribution at all future moments. The universe's entire space-time structure is fixed by initial conditions and equations. Solutions to Einstein's equations represent complete four-dimensional spacetimes from beginning to end, not three-dimensional spaces evolving unpredictably. The block universe interpretation takes this seriously. All moments exist simultaneously in determined relations, with nothing genuinely uncertain or open. Thermodynamics appears probabilistic, but might be fundamentally deterministic. Statistical mechanics derives thermodynamic laws from underlying microscopic dynamics. Entropy increase is overwhelmingly probable because vastly more microstates correspond to high entropy macrostates than low entropy macrostates. But individual particles follow deterministic laws. If you knew every particle's position and velocity exactly, you could in principle compute their future evolution deterministically. The apparent randomness in thermodynamics reflects ignorance about microscopic details, not fundamental indeterminism. A Laplace demon could predict exactly which direction entropy would increase, and by how much at every moment. Quantum mechanics introduces apparent indeterminism through wave function collapse. Before measurement, quantum systems exist in superpositions of multiple states. Upon measurement, the wave function collapses to a definite state randomly according to probabilities given by squared amplitudes. This collapse seems genuinely random. Einstein's God does not play dice. But many physicists reject collapse as fundamental. The many-worlds interpretation maintains determinism by suggesting wave functions never collapse instead. Measurement creates branches where all outcomes occur. The Schrödinger equation evolves deterministically. Apparent randomness reflects our ignorance about which branch we inhabit, not genuine indeterminism. Bohm's pilot wave theory also maintains determinism through hidden variables guiding particle motion. If determinism holds, the universe's fate was sealed at the Big Bang. Every star's formation, every supernova explosion, every galaxy collision was predetermined by initial quantum fluctuations. Your birth was inevitable given preceding conditions. Your thoughts right now reading these words are deterministic consequences of brain states determined by neuron firing patterns, determined by biochemistry, determined by atomic interactions, determined ultimately by the Big Bang. Nothing could be otherwise. When the last star dies trillions of years hence, that death was already encoded in the universe's first moments. Heat death is not something that might happen, but something that must happen, already implicit in cosmic initial conditions. This creates profound implications for meaning and responsibility. If everything is determined, do we have moral responsibility for actions we could not avoid? Compatibilists argue, yes, responsibility is compatible with determinism because our decisions are still ours, even if determined. Hard determinists say no genuine responsibility requires could have done, otherwise possibilities that determinism denies. The debate is ancient and unresolved. But regardless of moral implications, determinism suggests the universe is dead in a deep sense. It is not exploring possibilities or creating genuine novelty. It is computing the consequences of initial conditions, executing a program written at birth, following tracks laid down 13.8 billion years ago, leading inexorably to already determined conclusions. The future already written means the universe is a story already told, a movie already filmed, a book already published. We experience it page by page, frame by frame, but the ending is already there waiting. The universe does not become it is. Its entire history exists as a determined structure. Asking if the universe is dead might be asking whether this determined structure contains regions we label as alive, or regions where genuine openness and creativity exist. If determinism is true, the answer is no. The universe is dead because it cannot be otherwise than it is, cannot choose different paths, cannot create genuinely new possibilities. Everything that will be was always going to be. The universe unfolds inevitably toward predetermined heat death, and asking whether it could go differently is meaningless. It could not. The future is already written, the story already finished, the universe already dead, in the sense that its fate was determined before stars formed, before life emerged, before consciousness arose to question whether anything could be different than the determined path leads. Quantum immortality and observer moments. If the many worlds interpretation is correct, and reality constantly branches into parallel universes representing every quantum outcome, then a strange possibility emerges. You might be effectively immortal from your subjective perspective. In branches where you die, you cease experiencing. But in branches where you survive, you continue experiencing. Since you can only experience branches where you exist, you will only ever experience survival regardless of how improbable. This is quantum immortality, the idea that consciousness necessarily follows branches where it persists, making death unobservable from first-person perspective, even though observers in other branches see you die. If true, this means we are already living in a dying universe, but can never experience its final end. Consciousness will always find itself in branches where observation continues, even as the universe dies around us. The argument proceeds from the many worlds interpretation's ontology. Every quantum measurement causes the universe to split into branches representing each possible outcome weighted by quantum probabilities. When an atom decays, reality branches into one universe where it decayed and another where it did not. Crucially, observers split too. After the measurement, there are two versions of you in different branches. One observing decay, one observing no decay. Both are equally real. From the outside, both exist. But from inside, each version experiences only one outcome and is unaware of their counterpart. Apply this to life and death. Consider a quantum event that determines survival or death. Perhaps a quantum fluctuation in a neuron affects a decision to cross the street, leading to being hit by a car in one branch and safe passage in another. In the death branch, you cease experiencing. Your consciousness ends. But in the survival branch, you continue. Since dead branches contain no observer, you cannot experience them. You only experience branches where you survive. From your perspective, you always survive, even though external observers see you die in some branches. Consciousness necessarily follows survival branches because it cannot follow death branches where it does not exist. Extend this reasoning to cosmic death. As the universe approaches heat death and conditions become increasingly inhospitable to consciousness, Quantum branching ensures some branches maintain conditions supporting consciousness longer than others. In most branches, consciousness might go extinct as stars fade and energy gradients flatten. But in rare branches, improbable quantum fluctuations might maintain or create conditions supporting information processing. Quantum immortality suggests conscious observers will find themselves in these improbable branches regardless of how unlikely, because only those branches contain observers to experience them. From the inside, consciousness always persists even as the universe overwhelmingly trends toward death. However, quantum immortality faces serious objections. First, the argument assumes consciousness is fundamentally binary, either present or absent, rather than admitting degrees. But consciousness might fade gradually as brain function degrades. What happens to quantum immortality if consciousness dims slowly rather than switching off? Second, the argument assumes consciousness necessarily follows some branch, even if that branch is fantastically improbable. But extremely improbable branches have correspondingly small quantum measure. Advocates of self-indication assumption might argue consciousness should find itself in high-measure branches, not low-measure survival branches. Third, quantum immortality seems to predict we should observe increasingly bizarre circumstances as we survive ever more improbable events. We do not observe this. Moreover, quantum immortality provides no comfort regarding the universe's death. Even if consciousness always finds itself in some surviving branch, the vast majority of measure concentrates in branches where consciousness goes extinct. From the God's eye view encompassing all branches, consciousness dies in almost all branches as the universe approaches heat death. Quantum immortality at best says there is always some branch containing consciousness, but this branch becomes increasingly bizarre and improbable. It is like saying you never die because in some branch you survive as a Boltzmann brain spontaneously fluctuating into existence, technically true but not meaningful survival. The many worlds framework more generally affects how we think about the universe being dead. If reality constantly branches, then the universe does not have a single state but a vast ensemble of states across branches. In some branches, the universe is vibrant and alive. In others, it has reached heat death. In many branches, conditions vary between these extremes. Asking if the universe is dead becomes asking what fraction of measure occupies dead branches versus alive branches. Currently, most measure probably occupies branches with stars shining and structure persisting. In the far future, most measure occupies dead branches. But some tiny measure always occupies branches with improbable pockets of life or consciousness. This creates a strange situation where the universe is simultaneously alive and dead across branches, with the balance shifting toward death over time. From within any branch, observers experience one trajectory, but the totality encompasses all trajectories. The universe's death is not a single event, but a probabilistic process where measure flows from alive branches to dead branches as entropy increases and structures dissolve. Consciousness tracks alive branches, potentially following improbable survival branches indefinitely through quantum immortality, but with decreasing measure and increasing bizarreness. Ultimately, quantum immortality and many worlds do not prevent the universe from dying. They just suggest consciousness might persist in ever more improbable branches as the bulk of reality transitions to death. This is like being immortal by virtue of always inhabiting the most improbable survival branches. Technically, you never die from your perspective, but the vast majority of reality moves on without you into death. The universe is dying. Consciousness in most branches dies with it, and only by retreating into increasingly improbable pockets does consciousness persist. This is death with a tiny asterisk, not genuine survival. The universe dies. and consciousness mostly dies with it, leaving only ghosts in improbable branches, experiencing increasingly absurd conditions. This is not life, but the last gasps of observers clinging to existence in universes that have already moved beyond them into death. We exist in a cosmic graveyard. Look around at the night sky. What you see is not a living cosmos, but a vast graveyard, populated by the dead and dying. Most stars you observe no longer exist in their observed states. They have evolved, died, or exploded since emitting the light reaching your eyes. The galaxies you see through telescopes existed billions of years ago in forms long since transformed or destroyed. The cosmic microwave background is fossil radiation from a universe that ended 13.8 billion years ago. The very atoms in your body are remnants of dead stars, scattered as ashes through space. We exist surrounded by ghosts and ruins, mistaking these ancient echoes for living reality. The universe is already a graveyard, and we are merely late arrivals, wandering among the tombs, reading epitaphs written in ancient light. Consider Betelgeuse, the red supergiant star marking Orion's shoulder. It lies approximately 550 light-years away. The light we observe left Betelgeuse around 1470 CE, while Earth was in the Renaissance. But Betelgeuse is dying. It has exhausted hydrogen in its core and begun fusing heavier elements, causing it to swell into a red giant. Calculations suggest it could explode as a supernova anytime within the next 100,000 years. It might have already exploded centuries ago, but we will not know until the light from that explosion arrives. When we look at Betelgeuse, we might be observing a star already dead, a ghost, shining in the sky. Final photons from an explosion that occurred, but whose announcement has not yet reached us. We worship corpses when we admire Betelgeuse's reddish glow. Extend this to more distant objects. Supernova SN 1987A appeared in the Large Magellanic Cloud in February 1987, visible to naked eye observers in the southern hemisphere. The explosion actually occurred 168,000 years earlier. The star that exploded San Angelique -69 degrees 202 has been dead for over 150,000 years. When light reached Earth, human civilization was young. We observed an explosion that was ancient history in the star's reference frame. Now, decades after observing the initial blast, we watch the supernova remnant expand, the corpse's decay occurring in slow motion, each new observation showing a death that finished millennia before humans existed. Galaxies we observe are similarly defunct. The Andromeda Galaxy lies 2.5 million light-years away. We see it as it existed 2.5 million years ago in the Pliocene epoch, before modern humans evolved. Andromeda as it exists now is completely unknown. It might be merging with another galaxy, might be experiencing a burst of star formation from recent gas accretion, might be quiet and quiescent. We cannot know for 2.5 million years when current state photons arrive. We observe Andromeda's ancient past, not its present. The same applies to all distant galaxies. We observe historical states, not current reality. The universe we see is a museum of extinct forms preserved in light still traveling toward us. The Hubble Ultra Deep Field exemplifies this. This famous image captured 10,000 galaxies in a patch of sky smaller than the Moon's diameter as seen from Earth. Most galaxies in the image existed when the universe was young. Many are seen as they were over 10 billion years ago. Those galaxies have evolved dramatically since. Some merged into larger galaxies. Some exhausted their gas and stopped forming stars. Some were disrupted by interactions or tidal forces. The galaxies we see in the deep field no longer exist in their observed forms. We look at ancestral galaxies, progenitors that have long since transformed into descendants we cannot observe because light from their current states has not reached us. The deep field is a cemetery photograph, a picture of the dead taken when they lived, but viewed long after they died. Even nearby astronomical objects are ghosts. The sun, as we observe it, is how it appeared 8 minutes and 20 seconds ago, already past tense. If the sun exploded this moment, we would not know for 8 minutes. We would see the sun shining normally, receive its light and heat, and be completely unaware that it had died. For 8 minutes after solar death, we would live in a universe where the sun was already dead but appeared alive. We always observe the sun's corpse with 8-minute delay. We never see the sun now, only its past self, a delayed image reaching us from an object that exists in a state we cannot observe until light from that state arrives. The atoms comprising Earth and our bodies are literally graveyard material stellar ashes scattered through space and reassembled. Every carbon atom in your body was forged in a star's core through helium fusion. That star eventually died, exploding as a supernova or shedding its envelope as planetary nebula. The explosion scattered carbon into interstellar space where it drifted for millions or billions of years. Eventually, the cloud of gas and dust containing that carbon collapsed to form the sun and planets. Earth accreted from this material. Life arose, incorporating the carbon into molecules, cells, and eventually your body. You are made of corpses' atoms extracted from dead stars, purified through death and dispersal, reformed into new structures but retaining their history as stellar remains. The cosmic microwave background is the universe's corpse-light thermal radiation from plasma that existed 13.8 billion years ago but no longer exists. The CMB photons were emitted when the universe transitioned from opaque plasma to transparent neutral atoms. That plasma is long gone. It recombined into atoms that eventually formed galaxies and stars and planets and people. The state that emitted the CMB does not exist anymore. We observe fossil radiation from a universe that died cooled, expanded, transformed into something unrecognizable. The CMB is a ghost image of the early universe, preserved in traveling photons that took billions of years to reach us, arriving long after their source evolved into current cosmic structure. We exist in a cosmic graveyard because everything we observe is already past, already transformed or destroyed or evolved beyond its observed state. The living universe, as it actually exists now, is forever hidden by light's finite speed. We can only observe the dead objects as they were, not as they are. The universe might be alive in its present state, but we cannot see that present. We see only past, and in that past, everything observed has since changed or ended. The stars are dead, the galaxies are ghosts, the background radiation is fossil light, our atoms are stellar ashes. We live among the dead, observing the universe's history through its corpse light, surrounded by ruins and remnants, inhabiting a cosmic cemetery where nothing observed still exists in observed form. We are gravekeepers tending tombs of light, archaeologists excavating ancient photons, mourners at a funeral that has been ongoing for billions of years. The universe is already dead in the sense that everything we see is already gone, replaced by present states we cannot observe and future states we can only anticipate with growing certainty of inevitable heat death. Dark energy accelerating the end. Dark energy, the mysterious component comprising approximately 68% of the universe's total energy density, drives accelerating cosmic expansion that hastens the universe's transition toward a cold, dark, isolated final state. Discovered in 1998 through observations of distant supernovae, dark energy produces gravitational repulsion, effectively anti-gravity, causing space itself to expand at ever-increasing rates. This acceleration has profound consequences for cosmic structure and evolution. It prevents new large-scale structure formation, disrupts existing structures by pulling them apart, and ultimately will isolate all regions beyond our local group, beyond observational horizons. Dark energy is not merely a passive component, but an active agent accelerating the universe's death. The simplest model treats dark energy as Einstein's cosmological constant, a constant energy density inherent to space itself. As space expands, more space forms, creating more dark energy, while matter and radiation dilute. Dark energy's density remains constant, while other energy forms thin out. Consequently, dark energy's fractional contribution to total energy density increases over time. 5 billion years ago, matter and dark energy contributed equally. Today, dark energy dominates at 68%. In the future, dark energy's dominance will approach 100% as matter dilutes to negligibility. The universe's evolution becomes increasingly controlled by dark energy's properties. Dark energy's gravitational repulsion counteracts gravity's attractive force. On small scales within galaxies and galaxy clusters, gravity dominates and structures remain bound. But on scales exceeding approximately 100 million light-years, dark energy overcomes gravity. This scale is called the Hubble radius, where recession velocity due to expansion equals light speed. Beyond the Hubble radius, expansion carries regions apart faster than light. Dark energy's dominance means the Hubble radius shrinks over time, fewer regions remain gravitationally bound, while more regions separate beyond interaction range. The observable universe paradoxically shrinks even as space expands, because accelerating expansion pushes distant regions beyond observational horizons. This creates cosmic event horizons, boundaries beyond which light emitted now will never reach us even given infinite future time. The event horizon currently lies at approximately 16 billion light-years. Galaxies beyond this distance emit light that will never reach Earth, because expansion carries them away faster than photons can approach through expanding space. About 95% of currently observable galaxies lie beyond the event horizon. We see them only because we observe ancient light emitted billions of years ago when they were closer. Their present states are forever hidden. Any events occurring there now, stellar explosions, galaxy mergers, potential civilizations, cannot causally affect us, nor we them. These regions have effectively exited our universe. Over hundreds of billions of years, accelerating expansion will cause all galaxies, except those in our local group, to cross the event horizon and vanish from observability. The Andromeda Galaxy and Milky Way are gravitationally bound and will merge. The Triangulum Galaxy and dozens of dwarf galaxies are also bound. This local group will remain observable and eventually merge into a single, large, elliptical galaxy. But everything else, the Virgo cluster, Coma cluster, distant superclusters, the billions of galaxies filling the observable sky, will disappear as accelerating expansion carries them beyond reach. Future astronomers will observe only their merged galaxy surrounded by darkness, with no evidence of the wider cosmos we see today. Dark energy also affects cosmic evolution timescales. Without dark energy, the universe might eventually recollapse in a big crunch, or expand forever but decelerating, allowing structure formation to continue longer. With dark energy, structure formation has effectively ended. New galaxy clusters will not form, superclusters will not collapse into bound systems. The cosmic web is being pulled apart rather than continuing to grow. Dark energy has short-circuited cosmic evolution, preventing developments that might have occurred in its absence. The universe has been forced into a particular trajectory, eternal accelerating expansion, leading to cosmic isolation and heat death by dark energy's presence. If dark energy is truly constant as a cosmological constant, this fate is sealed. Expansion will accelerate forever, event horizons will shrink, observable universe will reduce to local group merger remnant, temperature will approach absolute zero, entropy will maximize, heat death will be reached. But if dark energy evolves, if its density changes, or its equation of state parameter W differs from -1, different fates become possible. Phantom energy with W less than -1 would lead to Big Rip, where expansion tears apart everything, including spacetime. Quintessence models where dark energy weakens might allow eventual recollapse. Current observations constrain W to approximately -1 with a few % uncertainty, consistent with cosmological constant but not definitively proving it. Future observations will measure dark energy properties with greater precision. The Vera Rubin Observatory, Euclid Space Telescope, and Nancy Grace Roman Space Telescope will map cosmic structure and expansion history to determine W and whether it changes with time. If W is measured significantly different from -1, our understanding of the universe's fate will change. For now, observations suggest dark energy behaves as a cosmological constant, implying eternal acceleration and heat death. Dark energy represents the universe's death sentence, an inexorable force pulling everything apart, isolating regions, preventing new structure, accelerating the march toward cold, empty equilibrium. It is not merely that the universe is dying dark energy, ensures it dies in a particular way, accelerating the process beyond what would occur from entropy alone. Black holes consuming what remains. Black holes represent the ultimate fate of massive stars and the final repositories for matter in galaxy centers. Over cosmic time, black holes grow by accreting surrounding material and merging with other black holes during galaxy collisions. Eventually, black holes will contain most of the universe's mass that has not dispersed into intergalactic space or been converted to radiation. During the black hole era, from approximately 10 to the 40th to 10 to the 100th years, black holes dominate the universe's mass energy budget. They represent concentrated matter in an otherwise empty expanding void. But black holes themselves are temporary, they evaporate through Hawking radiation, ultimately returning their contents to space as thermal radiation. Black holes consume matter only to eventually radiate it back in maximally entropic form. Stellar mass black holes form when massive stars exhaust fusion fuel and collapse. Stars exceeding approximately 20 solar masses can produce black holes through core collapse supernovae. These stellar black holes typically range from a few to tens of solar masses. Thousands or millions exist in typical galaxies. They grow slowly by accreting gas and occasionally consuming stars that wander too close. Binary black hole systems can merge when gravitational wave emission removes orbital energy, producing a larger black hole. These stellar mass black holes constitute a significant fraction of galaxies' dark, compact objects. Supermassive black holes reside at galactic centers with masses ranging from millions to billions of solar masses. Nearly every large galaxy harbors a supermassive black hole. The Milky Way's central black hole, Sagittarius A star, contains approximately 4 million solar masses. The supermassive black hole in Messier 87, imaged by the Event Horizon Telescope, exceeds 6 billion solar masses. These giants form through complex processes, perhaps from direct collapse of massive gas clouds, or growth from stellar black hole seeds through accretion and mergers, or combination of both. Supermassive black holes grow as galaxies merge, with the black holes spiraling together and merging into even larger black holes. Over cosmic time, more matter falls into black holes. Stars in galactic nuclei scatter through gravitational interactions, with some trajectories leading into the central supermassive black hole. Gas clouds, falling toward galactic centers, feed black holes. Galaxy mergers bring multiple supermassive black holes together to merge. The fraction of galactic mass contained in black holes increases from less than 1% currently to potentially tens of percent or more by the time stars fade. In the far future, after stars die and galaxies evaporate, supermassive black holes will remain as the dominant massive objects, surrounded by scattered stellar remnants and diffuse gas drifting through expanding voids. Black holes are entropy repositories. Bekenstein and Hawking demonstrated that black hole entropy is proportional to event horizon surface area in Planck units. A solar mass black hole contains entropy of approximately 10 to the 54th. A billion solar mass supermassive black hole holds entropy exceeding 10 to the 77th, vastly more than any other known object. When matter falls into a black hole, the universe's total entropy increases dramatically. The matter's organized information becomes encoded on the two-dimensional event horizon in maximally entropic configuration. Black holes represent thermodynamic endpoints matter cannot reach higher entropy without escaping the black hole. But black holes are not eternal. Stephen Hawking calculated that quantum effects near event horizons cause black holes to emit thermal radiation, losing mass in the process. This Hawking radiation has temperature inversely proportional to mass. Larger black holes are colder, smaller holes are hotter. For stellar mass and supermassive black holes, Hawking temperature is extraordinarily low, far below cosmic microwave background temperature. These black holes currently absorb more energy from surroundings than they emit, but as the universe expands and cools, background temperature will eventually fall below Hawking temperature. Then black holes begin net evaporation. Evaporation timescales scale as mass cubed. A solar mass black hole evaporates in approximately 10 to the 67th years. A supermassive black hole with a billion solar masses persists for roughly 10 to the 100th years. As black holes evaporate, they grow hotter. The temperature is inversely proportional to mass, so shrinking black holes radiate faster in a runaway process. Final evaporation occurs explosively when the black hole shrinks to microscopic size with enormous Hawking temperature. The black hole converts its remaining mass to a burst of particles and radiation, returning to space what it consumed over cosmic ages. After all black holes evaporate around 10 to the 100th years, their mass energy has been converted to dilute thermal radiation dispersed through expanding space. The concentrated matter that fell into black holes now exists as the lowest entropy configuration possible uniform radiation at near absolute zero. Black holes are consumption machines that temporarily concentrate matter and entropy on event horizons before ultimately dispersing both as featureless thermal radiation. They accelerate the universe's death by converting structured matter into disordered radiation, bringing heat death closer with each particle they consume and each photon they emit. Black holes represent not preservation but digestion. Matter goes inorganized, comes out maximally disordered, hastening the universe's inevitable decline toward entropic equilibrium. Cosmic microwave background fading relic. The cosmic microwave background radiation, abbreviated CMB, represents the oldest light in the universe, photons released approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this recombination, the universe was opaque free electrons, scattered photons continuously. After recombination, photons decoupled from matter and streamed freely through space. These photons, initially emitted as visible and ultraviolet light from 3000 Kelvin plasma, have traveled for 13.8 billion years. Cosmic expansion stretched their wavelengths, redshifting them through infrared into microwave frequencies. Today, the CMB appears as nearly uniform 2.725 Kelvin radiation, pervading all of space the cooled remnant of the universe's hot youth. The CMB provides crucial evidence for Big Bang cosmology and cosmic evolution. Its near-perfect blackbody spectrum matches theoretical predictions with extraordinary precision. Tiny temperature fluctuations at parts per 100,000 level reveal density variations that seeded galaxy formation. Satellites like COBE, WMAP, and Planck mapped these fluctuations, determining cosmic parameters including age, composition, and geometry. The CMB's properties support inflation theory, confirm dark matter's existence, and validate the hot Big Bang framework. Without the CMB, modern cosmology would lack its strongest empirical foundation. But the CMB is fading gradually but irreversibly diminishing as cosmic expansion continues. As space expands, CMB photons redshift to longer wavelengths and lower energies. The temperature decreases inversely proportional to the universe's scale factor. When the universe doubles in size, CMB temperature halves. Currently, at 2.725 Kelvin, the CMB will cool to 1.36 Kelvin when the universe doubles in size approximately 14 billion years from now. It will reach 0.27 Kelvin within 70 billion years. Eventually, the temperature approaches absolute zero asymptotically as expansion continues forever. As CMB temperature decreases, detection becomes increasingly difficult. Currently, CMB photons have wavelengths around 1 millimeter easily detected by radio telescopes. But as redshift continues, wavelengths stretch to centimeters, meters, kilometers, and eventually light years. Detecting radiation at meter wavelengths requires large antennas and is hindered by terrestrial radio interference. At kilometer wavelengths, detection becomes impractical with conceivable technology. The CMB effectively vanishes from observability within hundreds of billions of years as wavelengths exceed practical detection limits and photon energies fall below thermal noise. The CMB's fade-out has profound implications for future cosmology. Within 1 trillion years, the CMB will be undetectable, its photons redshifted to wavelengths measured in light years with energies infinitesimally above absolute zero. Future civilizations arising after the CMB fades will lack crucial evidence for the Big Bang. They cannot observe the uniform background radiation confirming the hot, dense early universe. They cannot measure CMB temperature fluctuations, encoding information about cosmic structure formation. They cannot use CMB polarization to study inflation and gravitational waves. Key evidence supporting modern cosmology will have literally vanished, erased by expansion's relentless redshifting. This creates disturbing epistemological implications. If critical evidence disappears over time, what evidence was available to earlier observers that has already vanished beyond our access? The universe might have passed through earlier phases, leaving signatures that have redshifted beyond detection or dispersed beyond recovery. Perhaps crucial clues about cosmic origins existed in the first millions of years, but have long since faded. Our cosmological understanding might be fundamentally incomplete, not from lack of intelligence, but from residing in an epoch where certain evidence no longer exists. Conversely, we are fortunate to exist when CMB remains detectable. The CMB is observable now because we live relatively early in cosmic history, only 13.8 billion years after the Big Bang, before expansion has redshifted it beyond detection. Had intelligent life emerged trillions of years later, cosmologists would face a far more challenging task, reconstructing cosmic history without CMB evidence. They might still deduce the Big Bang through other means: galaxy recession, light element abundances, theoretical considerations, but they would lack the direct observational confirmation we possess. The CMB's fading illustrates that observational reality changes with cosmic epoch. Earlier observers had access to phenomena we cannot see. Perhaps the universe's first moments left signatures visible for brief periods that have long since vanished. We observe phenomena that future observers will miss. The universe's properties change over time, altering what can be observed. Scientific knowledge is contingent on cosmic timing. The CMB, fading from detectable microwave background to invisible radio whisper, to undetectable ultra-long wavelength noise, represents the universe dying in an observational sense, evidence of its hot, vibrant past, gradually erasing itself through expansion, leaving future epochs in increasing ignorance about cosmic origins. We observe a universe already beginning to forget its own past, with memories fading as the CMB cools toward invisibility. The great silence, no new beginnings. The universe is characterized by a great silence, an absence of new fundamental processes, new types of phenomena, or new physics emerging from existing conditions. Everything interesting that will happen is basically just playing out consequences of things that already happened. The Big Bang set initial conditions. Inflation established large-scale structure. Nuclear reactions in the first minutes set light element abundances. Recombination released the CMB. Galaxy formation proceeded from density fluctuations. Stars formed from gravitational collapse. Planets coalesced from protoplanetary disks. Life emerged from chemistry. Intelligence arose from biology. These were one-time events or processes that have already concluded or are winding down. Nothing comparable will happen again. The universe has exhausted its repertoire of new tricks. No new fundamental forces will emerge. The four known forces, gravity, electromagnetism, weak nuclear, strong nuclear, have operated since shortly after the Big Bang, when symmetry breaking separated them from unified origins. These forces govern all interactions. Their coupling constants are fixed. Their behaviors are understood. No evidence suggests additional forces will manifest. The universe is not evolving toward new physics. It is playing out the consequences of existing physics established in the first moments. No new types of particles will form naturally at low energies. The Standard Model describes all known elementary particles. These particles formed in the early universe when temperatures exceeded their rest mass energies. As the universe cooled below particle formation thresholds, new particle production ceased. Currently, the universe is far too cold to produce massive particles naturally. High-energy cosmic rays occasionally create exotic particles in collisions, but these decay almost immediately. The stable particles, protons, electrons, neutrinos, photons, persist, while all exotic particles have long since decayed. The universe's particle zoo has been determined since the first seconds. No new residents will join. No new structures larger than current galaxy clusters will form. The cosmic web reached its maximum complexity approximately now. Dark energy prevents further clustering on scales exceeding current largest structures. Galaxy clusters will not merge into superclusters because expansion drives them apart faster than gravity pulls together. The hierarchy of structure planets, stars, galaxies, clusters has topped out. Nothing larger will assemble. Future evolution involves dissolution rather than construction, as existing structures slowly dismantle through evaporation, dispersal, and consumption by black holes. No new stellar types will emerge. The stellar classification sequence O, B, A, F, G, K, M classes, based on temperature and mass, encompasses all possible hydrogen-burning stars. Brown dwarfs occupy the substellar regime. White dwarfs, neutron stars, and black holes are stellar remnants, not new stellar types. The universe has explored the full range of stellar possibilities. Future stars will be chemically enriched with heavier elements from previous generations, but their fundamental types remain unchanged. No new stellar phenomena will occur that have not already occurred countless times. No new biochemical frameworks will likely emerge. Life on Earth uses DNA, RNA, and proteins in carbon-based chemistry powered by chemical gradients. Alternative biochemistries might exist elsewhere, silicon-based, using different solvents, employing different information storage, but the space of possible biochemistries is finite and bounded by chemistry's laws. If life emerges multiple times across the universe, it will sample these possibilities, but it will not invent fundamentally new chemistry. The periodic table is fixed, chemical bonding rules are unchanging. Life will work within these constraints, just as all terrestrial life does. No new types of intelligence or consciousness, fundamentally different from what already exists or could exist, will emerge. Intelligence arises from information processing in complex systems, whether biological brains, artificial neural networks, or exotic substrates. Intelligence operates through computation, memory, and feedback. The space of possible minds is large but bounded by computational principles. Superintelligent AI might vastly exceed human intelligence, but will not be a fundamentally different category, just more powerful implementation of the same principles. Consciousness, whatever its nature, operates within physical law. No new category of mentality will emerge that is not in principle possible now. The universe's future is not a journey toward novelty, but an unwinding of initial conditions. The Big Bang contained everything needed to produce everything that followed. Initial quantum fluctuations contained all information required to produce cosmic structure. Physical laws established in the first moments govern all subsequent evolution. The universe is not discovering new things, it is computing the consequences of its starting configuration. This represents a deep sense in which the universe is already dead. It is not growing or evolving toward new states, but merely executing a predetermined or probabilistically determined program established at birth. The Great Silence is the absence of genuine novelty, the lack of new beginnings, the recognition that everything interesting has already been initiated, and future consists only of developments already implicit in the past. We are living in the afterglow. We exist during the universe's afterglow, the fading light from events that occurred billions of years ago, the residual warmth from a hot beginning that has cooled dramatically and continues cooling, the echo of a violent birth that has quieted to near silence. The cosmic microwave background is literally afterglow thermal radiation from the universe's hot youth, now cooled to 2.7 Kelvin. The stars we observe shine with light emitted years to billions of years ago. The elements in our bodies were forged in stellar cores that exploded as supernovae before the sun formed. The very structures we inhabit, planets, solar systems, galaxies, are consequences of processes that peaked billions of years ago. We are not witnessing the universe's prime, but its declining aftermath. The CMB represents the most obvious afterglow. These photons were emitted 8 billion years ago from 3,000 Kelvin plasma filling the universe. They have been traveling ever since, cooling through cosmic expansion. When detected today at 2.7 Kelvin, they carry information about conditions 380,000 years after the Big Bang, but nothing about the intervening 13.8 billion years. The CMB is fossil light, a preserved remnant of the early universe, not a living signal. It is afterglow in the truest sense, the fading luminescence from an event long concluded. Stellar light similarly represents afterglow. The sun's photons were generated in its core through fusion reactions occurring over the past tens of thousands to millions of years as energy diffused outward. The sunlight illuminating Earth left the sun's surface 8 minutes ago. When we observe distant stars, we see them as they were years to thousands of years ago. Some stars we see have already died, but their light continues propagating, arriving at Earth to create the illusion of a living star. We bask in the afterglow of stellar furnaces that burned long ago, mistaking ancient photons for present reality. The heavy elements comprising Earth and our bodies are afterglow of stars that died before the sun formed. Carbon, nitrogen, oxygen, silicon, iron, all elements heavier than hydrogen, and helium were synthesized in stellar cores through fusion and dispersed through supernovae. The atoms in your body were forged in stars that exploded billions of years ago. You are literally made of stardust debris from dead stars scattered through space, coalescing into the sun's protoplanetary disk, accreting into Earth, becoming incorporated into life. Your physical substance is afterglow, remnants of processes that concluded before your planet existed. Galaxy structure represents afterglow of processes that peaked billions of years ago. The cosmic web formed through gravitational clustering, following patterns established by quantum fluctuations during inflation. Galaxy formation occurred most vigorously when the universe was young. Major mergers that shaped large galaxies happened billions of years ago. The Milky Way's spiral structure reflects past star formation bursts and gravitational interactions. We observe the results of ancient processes, not ongoing construction. Galaxies are not being built, now they are coasting on momentum from earlier epochs, slowly evolving, but fundamentally already formed. Star formation peaked 10 billion years ago and has declined since. The Stelliferous era's most productive phase is past. Current star formation is afterglow residual activity using gas left over from earlier epochs. Most stars ever formed are already born. Future star formation will decline further until it ceases entirely. We live in the declining phase of stellar genesis, watching the final generations ignite from dwindling gas supplies, afterglow of the universe's stellar prime. Even life might be afterglow. If life emerges commonly in the universe, its peak occurrence might already be past. Conditions for life require stable stars, planets in habitable zones, and sufficient heavy elements for chemistry. These conditions were unavailable in the early universe, lacking heavy elements. They became common only after generations of stars synthesized and dispersed metals. But they will become rare in the future as stars die and planets freeze. Perhaps life flourishes during a window spanning roughly now billions of years after the Big Bang, but before stars fade. If so, we exist during life's cosmic epoch, which is itself afterglow of stellar nucleosynthesis and precursor to lifeless darkness. Intelligence and consciousness might similarly be temporary phenomena. Complex information processing requires energy gradients, stable environments, and sufficient time for evolution or construction. These conditions existed for billions of years, but will not persist as the universe approaches heat death. Intelligence might flourish during the Stelliferous era, but go extinct as stars fade. If so, consciousness is afterglow brief complexity arising during the universe's middle age, destined to vanish, leaving no descendants, no heirs, no continuation. All thought, all experience, all meaning would be temporary spark in eternal darkness after glow of stellar burning that will eventually fade to nothing. We live in the afterglow in every sense. The light we see is ancient. The matter we are made of is debris from extinct stars. The structures we inhabit are products of concluded processes. The conditions permitting our existence are temporary intersection of circumstances that will not last. We are not witnessing a universe in its prime, but one in its aftermath past peak, declining, coasting on residual energy and momentum from earlier epochs. The afterglow is beautiful, stars shine, life flourishes, complexity persists, but it is fading. The light dims, the warmth decreases, the glow weakens. Eventually, afterglow fades to darkness. We exist during the glow, perhaps near its peak, certainly before it fully fades. But the ending is inevitable. We are living in a dying universe's last light before eternal night. The universe's final breath. If the universe were a living entity taking its final breath, what moment would that breath represent? Perhaps it is now this present era, 13.8 billion years after birth, when stars still shine but star formation declines, when galaxies remain visible but accelerating expansion begins isolating them, when complexity persists but entropy inexorably increases, when life and intelligence exist but their futures appear bleak. This moment might be the apex of cosmic exhalation, the last gasp before silence descends. Or perhaps the final breath occurred billions of years ago, at peak star formation, peak energy output, peak complexity, with everything since being the slow release of that breath's last remnants. Or the final breath might lie in the future, when the last star dies, the last black hole evaporates, the last conscious thought occurs. Whenever it is, the universe's final breath is not violent explosion, but gentle exhalation energy slowly dispersing, structures gradually dissolving, complexity fading into simplicity. The metaphor of breathing implies cyclical process: inhalation, followed by exhalation, breath in, then breath out, continuous renewal. But the universe does not breathe cyclically. It had one breath, one expansion from the Big Bang's low entropy state, and is exhaling that breath over timescales spanning trillions upon trillions of years. If the Big Bang was inhalation, gathering energy into a tiny volume at enormous density, then cosmic expansion is exhalation, dispersing that energy across ever larger volumes at ever lower densities. The breath is not held and released, but continuously released in an exhalation lasting cosmological epochs. The universe's breath is observable in cosmic expansion. Space itself grows, carrying galaxies apart, diluting matter and radiation, cooling the cosmic microwave background. This expansion is the universe breathing out, releasing the energy and matter concentrated at birth into an increasingly vast volume. The Hubble constant quantifies the breath rate, currently approximately 70 kilometers per second per megaparsec. This rate changes over time as expansion accelerates. The breath quickens as dark energy drives faster expansion. But regardless of rate, the direction is outward, dispersing, cooling, exhaling. Entropy increase represents the breath's irreversibility. Inhalation could reverse exhalation if breath were truly cyclic. But entropy never decreases. The universe cannot breathe back in. It cannot reconcentrate dispersed energy, cannot reverse expansion, cannot decrease entropy. The second law forbids reversal. The breath is one-way process, exhale only, no inhale to follow. This makes the final breath truly final, not a pause before next breath, but the last emission before silence. The last stars represent the universe's last energetic releases, final exhalations of fusion energy before permanent cessation. When the last red dwarf exhausts hydrogen and fades, stellar fusion ends forever. When the last black hole evaporates in burst of Hawking radiation, the last significant energy release occurs. These are gasps, final outputs before quietude. After them, the universe has no more breath to release. It exists in maximum entropy equilibrium, having exhaled everything it had. Life and consciousness might be the universe's last conscious breath matter, organizing itself to experience its own existence before dissolution. If consciousness emerges from complexity, and complexity is temporary, then awareness is brief phenomenon during cosmic exhalation. Minds are vortices in the outflowing breath, temporary patterns in energy dispersal, briefly maintaining identity before dispersing back into flow. When the last conscious thought occurs, perhaps trillions of years, hence when energy gradients can no longer power information, processing the universe's subjective breath ends. Afterwards, the universe exists but does not experience. The breath continues objectively but without awareness. The final breath might already be behind us if peak complexity has passed. If the universe reached maximum information content, structure, and diversity billions of years ago at peak star formation and galaxy formation, then the final breath, the last maximum output, already occurred. Everything since is denouement, slow decline of a system already past its climax, releasing residual energy before falling silent. We exist during the decline, in the long tail after the peak, watching the breath's last remnants dissipate. Alternatively, the final breath might be now, this present epoch, when stars shine, planets orbit, life exists, complexity persists, but the end is already sealed and approaching. The universe balances between past vitality and future darkness, between structure and dissolution, between complexity and simplicity. This moment, any present moment, is the knife edge where the breath remains partly in but mostly out, where some energy remains concentrated but most has dispersed, where death is inevitable but not yet complete. Now is the final breath, in the sense of last moment containing both life and death in balance. Or the final breath lies in the far future, the last quantum fluctuation in heat-death equilibrium, the last virtual particle pair, briefly disturbing featureless uniformity before annihilating, the last event in a universe that has otherwise reached stasis. That would be the true final breath, the absolute last release of energy, last change, last process, before eternal perfect equilibrium. But by then, the breath is so faint, so rare, so meaningless, that it barely qualifies as breath at all, just statistical fluctuation in silence. The universe's final breath is not a moment, but a process, the entire trajectory, from Big Bang to heat death, from low entropy to maximum entropy, from concentrated to dispersed, from complex to simple. We exist within this breath, experiencing one phase of its long exhalation. The breath is dying in the sense that it is being expelled and will not be renewed. When fully exhaled, the breath is gone and the universe lies still. We live in the dying breath, perhaps near its end, certainly past its peak, watching it fade while knowing no breath follows. This is what it means for the universe to already be dead, not that it has stopped, but that it is stopping. Not that the breath has ended, but that the breath is ending and cannot be renewed. The final breath is now, was then, will be later. It is the entire process of dying we observe all around us.